So, good morning, all. I feel honored to welcome Dr. Arjyoti Goswami from NIT Durgapur for the first technical session on intelligent systems and smart technologies in mechanical engineering. Dr. Arjyoti Goswami is an assistant professor in the Department of Mechanical Engineering, NIT Durgapur. He works in the area of advanced manufacturing, polymer processing, micro and nano fabrication. Three PhD scholars have completed their PhD under his supervision. He has completed one DST ACRB funded project and has one patent in his name. In addition to these three book chapters, he has as well as 29 international journal papers and 12 international conference papers are presented by him. He teaches subjects related to welding, industrial engineering, advanced manufacturing, and etc. Now, I would like to hand over this session to Dr. Goswami, and I am sure we all will be enriched with the knowledge and enjoy the learning. So, sir, it is over to you. Please take the session.
Okay, am I audible?
Yes, sir, you are audible.
I will share the screen to share my PPT.
Okay, sir.
Kindly tell me whether the screen is visible or not. Okay, so I have shared
Yes,
it
sir.
now.
Yes, sir. It is visible.
Screen is visible, right?
So
Okay.
please make it full screen, sir. Please.
Yes, I'm putting it. I'm putting full screen.
Yes, sir.
Now
It is all over.
it is visible, right?
Okay.
Okay.
Okay. Thank you, sir. Continue.
So please tell me how much time I have. I have till 12:30.
You can take up to 12:30 to 12:45.
Okay. So I'll try to finish within 12:30 and we can
Okay.
have some questions if any.
Okay. Okay. Thank you, sir.
Okay.
Please
So
continue.
yes, I'll start now. Thank you for the invite. And as sir told already, this is the first technical session and much awaited session and all. So I am sort of the opening player. So there is a pressure on me. It is a little bit bigger PPT, around 65 slides are there. But at any point of time, if you feel that you want to ask something, please don't wait till the end of the PPT. You can just stop me and ask me what is going on, or if any queries you have, you can ask it. Most importantly, if you have any suggestions, because the things that I'm going to discuss are not highly technical. This is something that we are moving towards. So everyone has something to contribute in it. So if you feel that you want to add something or you want to correct me on any point, please do that. Okay, so I'll start now. So as can be visible on the screen, the topic of my PPT is intelligent systems and smart technologies in mechanical engineering. My name is Arjyoti Goswami, sir has already introduced. So the PPT is divided into three parts. Part one is we'll try to understand what is meant by intelligent systems and smart systems, because we use these terms a lot and we use it in various platforms. Nowadays, industry is trying to shift towards it. So we try to understand what is actually meant by these terms. I'll try to give you some examples, some definitions, which I found in different references. Second is, why do we want to go for intelligent and smart systems? So why is there a need for change? Because just because someone is saying that we have to go towards intelligent system, we should not be blindly following it. So what is the logic behind it? I'll try to explain it, why there is a need. Third is in mechanical engineering. So intelligent and smart systems, as you guys might imagine, as the esteemed faculties might imagine, that it is a inter-industrial thing. There is we cannot have it in an isolated fashion. All the entire industry has to adopt this system. But specifically, what is its relevance in mechanical engineering? I'll try to get to that. And while explaining it, you will observe that I will give references from different other industries also. It is only because mechanical engineering by itself cannot go into smart and intelligent manufacturing. If at all we as mechanical engineers, we want to go to that, we have to take help from electronics engineering, we have to take help from electrical engineering, we have to take help from suppose computer science and so on. So many other things are there that we should understand. And lastly, conclusions and discussions. So discussion, as I said, we can have it throughout. If at any point you feel like adding something or asking something, please do that. Make me stop and do that. Okay. So the part one, intelligent and smart system, will try to understand what is meant by intelligent smart system. What are the features of an intelligent system? When do we call that something is intelligent? And lastly, what is smart system? Why intelligent and smart? Why these are two different terms that we are using? Why can't we have only intelligent system? What is meant by smart system? That we'll try to make sense of. So what is an intelligent system? Intelligence, the very basic definition is intelligent people are those people, I'm telling from a human point of view initially. Intelligence is people are those people who can take good decisions, and those decisions they have to take those decisions in a changing circumstances, and they have to make the decisions at a very high speed, and they have to make the correct decisions. So if a person can take correct decisions when the situations are changing and when those decisions are right, then we say that that person is an intelligent person. For example, there is an administrator who is handling the office, and in the office some work is being carried out, and suddenly a problem has come up. Suppose the office is undergoing inspection, and on that day the electricity has gone out. This is a type of a situation that the supervisor or the administrator might not have anticipated. He might be thinking that, okay, today we have the inspection, everything should go correctly, which is correct, everything should go well. But suddenly some situation has changed. In such a situation, now the supervisor has to take a decision, what to do, how to handle this situation, and that decision has to be correct also. The supervisor cannot say light has gone, so let us close the office and go home. Inspector is coming, let him come. Light has gone, what do I do? Right? He cannot take such a decision. He has to take a decision in an emergency scenario. He has to take the decision at a high speed. Quickly, he has to take the decision, and he has to take the correct decision also. So, such a person who is able to do this thing, we call that person as an intelligent person. Okay. So, intelligent systems are also like that. Intelligent systems are systems which are capable of taking decisions in a changing circumstances, which means they don't already know what is going to happen. Something is coming up suddenly, and they have to make the decision very quickly, and they have to make the correct decision. So for an example, in professional domain, we have observed that during the corona crisis, during the COVID-19 pandemic situation, so many problems were there. People used to get checked in the medical nursing homes and everywhere, and they have to the doctors, they were already engaged. They have to take care of the patients who are suffering from the diseases. They have to give the medicine to those people and so on. In such a scenario, for the initial investigation, the doctors were not available. So that time, many data scientists, many scientists, they came up with codes. They came up with some kind of algorithm which can just take the input in the form of X-ray, and using that X-ray, they could figure out whether that person is suffering from corona or what kind of disease, right? So using that kind of intelligence, they were able to reduce the workload onto the doctors, onto the medical individuals, because doctors, nurses, the operators, everyone were very, very busy, right? Second type of intelligence is seen in the airport gate assignment. Suppose in our Durgapur airport, there is only 2 gates, right? But if it is a very big terminal, suppose it's a Delhi airport or Mumbai airport, so many gates are there. Their international flights are also going, domestic flights are also going. That time, while assigning the gate to a particular flight, if you have to allot a person, then it is like wastage of a resource. So they just have a system. They put in the flight number, they put in the flight timings, they put in the type of the flight, whether international flight or domestic flight, and then randomly they generate a gate number, and then they make the announcement that for the flight till Jodhpur, you go to gate number 2 or whatever, right? Another type of intelligence, which is a machine can do it, you don't need to assign a person, is randomization of polling personals, because nowadays election time is coming up. So we are in that election scenario, right? So you might have heard, and most of us who get the election duties, we are also aware that they do randomization, which means which particular person will have to do duty in what polling station, that is randomized. So they have softwares for it. They train that software. That software can be said to be an intelligent software. That software can take input in the in the form of number of polling personnel. They can take input in the number of polling stations available, and randomly it can assign. So that can be called as an intelligent system. And there are some other tedious tasks. For example, nowadays people want to develop autonomous driving, autonomous automobiles. For example, if a truck is driving for a longer time, if it is coming from, suppose, Amritsar, and if it is going till Meghalaya, so it is traveling a very large distance. So can we make trucks, and can we have a dedicated terminals, dedicated corridors for those trucks to move? And of course, giving something, giving a computer program to drive something is not very easy, right? So many different problems, different challenges can come up, but we have to train that system. We have to make that system intelligent enough so that it can take those decisions, and it can make those decisions very, very quickly. So that is one aspect, another aspect of the intelligent system. And then there are some dangerous tasks. For example, if you have to send a submarine to very large depth of the ocean, right? Very recently, all of us have heard that the submarine, it collapsed. I'm forgetting the name, Titan submarine or some submarine. A very big billionaire, he purchased that submarine, and they went to the depths of the ocean, and there it crumpled. So we lost the lives, right? That there are other dangerous tasks. For example, you want to see what is happening inside the volcano at the time of eruption, so that we can predict when the volcanoes will erupt. But obviously, human being cannot go over there. So can we develop some systems which can go inside, might be dormant volcano, or an active volcano, and take the data? And the other examples are Mars rover. So if we want to address such challenges, the system has to be intelligent. Now, what is an intelligent system? The very first feature of an intelligent system is that intelligent system has to operate in a complex environment. The environment cannot be something where everything is known and everything is constant. For example, a system which is just switching on a button and then letting the button switched on, it cannot be an intelligent system, right? If you write a program, you just program a motor, the motor will move, and then the switch will be on. This cannot be termed as an intelligent system. This is a sort of a mechanical system, a digital system, but this is not an intelligent system. So here the example I have given. So suppose nowadays people are coming up with the concept of smart homes. So in smart home, what we do is the person who is living inside the home, depending upon his activity, depending upon his metabolism, his age, his health condition, the thermostat, it senses the temperature inside the room. And then the thermostat is also fed some information regarding the person, that how old is the person, what is the climate in Durgapur right now, whether the AC has to be switched on or the fan has to be switched on. If the AC is switched on, how much temperature is needed, and so on. Everything will be programmed into that machine. And depending upon the situation, depending upon that particular instant of time, the thermostat will communicate with the controller. So in the schematic on the top side, I have written communication with the other agents. But as an example, I've said the thermostat is communicating with the controller, and then it is controlling the temperature. Okay, so it can generate more heat, it can generate less heat, it can open the fan, and so many other things it can do. If it is able to react based on the condition of the person at that particular instant, then we can say it is an intelligent system. Intelligent system, the condition in which it is functioning, it can be static or dynamic. Most of the time, intelligent system, we consider something as intelligent if it is functioning in a dynamic environment. Now, the changes which are happening, it can happen in a discrete manner, it can happen in a continuous manner. For example, the change in temperature, it is a continuous phenomenon, because right now the temperature is quite high, a person is feeling hot. Within 1 second, he will not start feeling cold. The temperature change will happen gradually. So the system, the intelligent system, we have to design in such a manner so that it can respond to the gradual change. But suppose suddenly something has short circuited and now the fire extinguisher has to be switched on. That change will be discrete change, right? We have to program the smart house. We have to design the smart house in such a manner so that it can figure out that whether sudden spike is there in a temperature. So that is a discrete change. Okay. So depending upon this, we can have different type of intelligent system. The changes can be fully observable, it can be partially observable. For example, in case of self-driving vehicles, the changes which are happening right in front of the car, those can be sensed by the vehicle. But if the changes are happening 1 kilometer down the road, that we cannot view. Okay, the changes can be deterministic, the changes can be stochastic. Deterministic means the changes can be expressed in the form of numbers. For example, if the temperature is going up or the temperature is going down, we can say the temperature has gone from 28 degrees Celsius to 35 degrees Celsius, which means the room has become hot. So you switch on the AC or you increase the cooling of the AC. Those are deterministic changes. But stochastic changes means something which cannot be determined in the number. For example, if a person is feeling depressed, so it is physiology that if a person is feeling depressed, his body will try to shut down. But if a person is feeling depressed, his state of mind, it cannot be quantitatively expressed. The AC of the room cannot realize if a person is depressed or not, what is his state of mind, what is his mood, right? But if a person is feeling depressed, then the temperature cannot be lowered. You cannot make the room colder, because in a cold climate, the person will get further depressed, right? So if a person is getting depressed, he will try to open the window, he will switch on all the lights, he will put on a motivating music or whatever the person will do, right? But it is very difficult for an intelligent system to sense when a person is feeling depressed. Such type of environment, when the thing cannot be expressed in numbers, that is called as a stochastic environment. Okay. Now, the changes which are happening, it can be episodic or it can be sequential. For example, episodic changes, they happen at a regular interval. For example, after every 12 hours, either sun will come up or the sun will come down, right? So these are called as episodic situations. So after every 12 hours, we can program our AC to make some changes, that after 12 hours, it will be 6 o'clock in the evening. So sun would have gone down. So temperature has to be a little bit increased. After 12 hours, it will be 6 in the morning. So morning will come up and the temperature has to be adjusted in that manner. So this is called as an episodic changes. Sequential environment means whatever is happening right now, it will influence the next instant. For example, if something is short-circuited, so if something is short-circuited, at the next instant, it will start damaging the home, right? So very quickly, the fire extinguisher has to come up. If the fire extinguisher is coming up, it will create a lot of smoke. So at the next instant, the smoke disperser, the vacuum has to be activated, right? So these are called as sequential changes. One by one thing will lead to another. This is sequential changes. And known changes and unknown changes. Most of our smart programming, intelligent programming is based on the idea that whatever is happening right now, we know what is going to happen because of it. For example, if a fire is breaking out, damage will happen. Extinguisher has to come, smoke will come. So we are predicting what is going to happen. But many times we cannot predict what is going to happen. For example, if a war is breaking out in the Gulf country, right, that time we cannot predict what is going to happen in our home, right? But still there is some functionality. For example, if a war is breaking out in the Middle East, then the Wi-Fi of my home should constantly be activated. Right? My Wi-Fi cannot shut down. My Wi-Fi has to be protected. So the system, the smart house has to be designed in such a manner that if a war is breaking out in some part of the world, then the Wi-Fi at my home should work very well, right? If there is only 1 unit of power left, that power must be diverted towards the Wi-Fi, because I want to know what is happening in the Middle East, right? And also there are other factors. My relative, they are staying in the Middle East. So I am much more interested in knowing what is happening over there. I am not interested in controlling the AC of my room using a code, right? I am much more interested in seeing what is happening in what part of the world. Similarly, during elections, the political parties, they want to know what is happening in that constituency, in that area and so on, right? So these are some examples of the system. Intelligent system, all of us might know this, that one type of intelligent system is quite easily available, that is a chess player algorithm, right? So the chess playing program, it is a static situation, it is a discrete situation, it is fully observable. If you have a good knowledge of chess, you can predict that what is going to happen in the next moves. It is a deterministic scenario, sequential, because one thing will lead to another, and it is a known scenario. Whatever type of move you are making, what is going to happen because of that move, you can predict. So that is a known scenario. But self-driving cars or self-driving vehicles, on the other hand, it is a dynamic scenario. The situation is continuously changing. And second point, it is a continuously changing scenario. Suddenly, hopefully, the road will not stop, right? As an engineer, we believe in logic. So if a road is there, suddenly a hole will not appear in the road. Of course, it might appear, but we hope that it won't appear, right? So while programming the car, will hope that hole will not be there. If you just make the car move in a straight line without violating traffic laws, without violating the speed limit, and the car will get to that particular point, right? But suddenly, if a hole is coming, suddenly the road is not there, suddenly a police person is coming and stopping the car, but there is no one inside the car to stop. The car is going past the police person, and then the police person is issuing a warrant. So many other things might happen, but that we are not concerned about. Right now, our self-driving car is not that level of intelligent, right? Third thing, the situation in the self-driving car is a partially observable situation. You can see what is there right in front of you. It is a stochastic situation. The condition of the road, the situation outside the road, it is not deterministic in nature. While determining the quality of the road, you cannot assign a number to it. You cannot say this road is 8 out of 10. Who will believe that this road is 8 out of 10? Ministers will say this road is 8 out of 10. The users will say this is minus 8 out of 10. Who to believe? You cannot believe, right? So stochastic situation is the condition of the road is based on your observation, right? The road might be very good before visit of big persons, but after the visit, the road will crumble. So as a driver who is driving your car, you're driving his own car, his or her own car, you have to realize the situation. You have to figure out ki kya hai, what is the situation of the road, and then you have to act accordingly. Okay, self-driving car, the problem is sequential. One thing will keep on leading to another. So if there is a hole in the road, and if the car is not adjusting itself, the car will drive over the hole. If the car drives over the hole, the suspension of the car might be having some problem. If the suspension is having the problem, then for the later part of the road, it will consume more fuel. If it consumes more fuel, before the next filling cycle, the fuel will run out, and so many other problems are there, right? And then known and unknown. So self-driving car, the problems is a combination of both known and unknown. Some of the situations, some of the problems which are going to arise are known in nature, but some of the problems are unknown in nature. Suppose you are driving the car and suddenly the traffic volunteer has come with a hand, oh, stop the car, stop the car. But the self-driving car cannot know, right, that who is coming or what is coming. You have to feed that information to him. So those things are unknown. But what is known to you? You know the route, that this route I have to follow. This is the corridor that I have to follow. This is the route that I have been programmed for. So the route is okay. The route is clear. But on this route, suppose suddenly a dog has come, because so many dogs are there, they can come. If suddenly a dog has come, as a driver, as a human driver, you will stop the car. But the self-driving program, the intelligent car, is not that much intelligent that it can account for sudden appearance of canines, of dogs, right? So it cannot account for that. So the self-driving car is a peculiar type of problem. Something is known, many things are unknown, and many important things are unknown. So you cannot just neglect. You cannot say, okay, I will drive over the dog. You cannot even say that, right? It is a criminal offense. So you, as an engineer, you have to figure out how to solve that problem. Okay. So what is an intelligent system? The second feature of an intelligent system is it should have basic cognitive capabilities. What is cognitive capabilities? Cognitive capabilities means it should be able to function in an environment. It should be able to take data from the environment, and it should be able to logically analyze the data, which means, for example, the example of the thermostat, it is functioning inside a home. It should have a sensor which will take the data from the home, that okay, this much is the temperature, and now it should analyze that okay, human body, the temperature is 37 degrees Celsius. Based on the past history of this person, he is most comfortable at 30 degree, but outside the temperature is quite high. Outside temperature is 35 degree. Human temperature is 37 degree. But this person has to be made comfortable. So let me put 29 degree. This kind of logical reasoning, this kind of analysis of the data should be there. It should be a feature of the intelligent system. So it should be able to deliberate on the data, and it should be able to interact with the other agents. Other agent in this case is the temperature controller, right? It should then give the signal to the temperature controller. This temperature controller will then execute the lowering of the temperature, and then the home will become cooler. Okay. So self-driving car, I have told you, self-driving car, the thing is there are much more number of data available. There is a data of the pedestrians, data of the traffic signals, data of vehicles, data of sudden appearance of dogs, data of police, data of crowd. So many things are there. That data has to be deliberated. That data has to be analyzed. That data has to be interacted with some other agency. For example, in case of self-driving car, that data has to be fed into the engine. That data has to be fed into the fuel control so that you can control the speed of the car. That data has to be fed to the motor, which is controlling the movement of the pedal. And then based on this data, the steering will be controlled, acceleration will be controlled, braking will be controlled, refueling cycle will be controlled, everything, those things will be controlled. Okay. Types of intelligent system. Intelligent system can be classified into two types. Autonomous system, which means it is functioning in an environment, taking the data, analyzing the data, and doing the action. So as a thermostat, it is seeing that temperature inside the room is high, garmi hai room ke andar, so let me just improve the cooling. So I will make the room cooler. That is autonomous system. Advisor system is, it will take the data and it will give you suggestions. It will not take a decision by itself. For example, all of us have used microwaves in our home, right? You put a dish inside a microwave, and you give a 30-second heating cycle. So after 30 seconds is over, and within the next 5 seconds, if you don't open the door, it will give out a beep. A beeping noise will be there, which means that time is over. Wherever you are, you come now and you take out the dish. If you are doing mobile, you leave the mobile, come and take the dish. So this is called an advisor system. Nowadays in cars also this system is available, right? So if you don't put the seat belt, the car, if the speed goes beyond 20 kilometers per hour, the car starts making some noise that you put on the seat belt. This is called as advisor system. The microwave does not open the door by itself. If the microwave had opened the door by itself, we would have called it as autonomous system. We have not reached that level of autonomous yet, right? So microwave does not open the door by itself. If you are driving without the seat belt beyond 20 kilometers per hour, the seat belt does not come out by itself. That I will make sure that you wear the seat belt. वो गले में ही बांध दिया पता लगा. So these things cannot happen, right? So this is an advisor system. So this is just the broadest possible definition. Intelligent system, it works in a global environment. It takes a lot of input. Those inputs are given to a lot of different agents. Those agents, they communicate with each other, and then they do the corrective action, whatever action they have to do. And the last thing of an intelligent system is it must exhibit complex intelligent behavior. For example, the intelligent system must exhibit rationality and it must exhibit learning. Rationality means the decisions that an intelligent system is taking, that a system is taking, must be based on logic. For example, temperature is going up, so let me increase the cooling. This is a logical decision, right? The decision must be based on learning. For example, based on the past history, at 11 o'clock in the morning, the temperature requirement is 28 degrees Celsius. So the system is making the temperature 28 degrees Celsius. This is called as rationality and learning. The decision is based on logic and the decision is based on past experiences. If a system can exhibit such level of handling the data, such level of deliberation and interaction, it is called as an intelligent system. Okay. Nowadays, if you have ever used ChatGPT, you will find that you ask something to the ChatGPT that this is my problem, what is the solution? So ChatGPT will give you the solution, but it will also ask you further questions. So it gives you the answer to the problem. It senses the situation, it understands the problem, and it gives the solution. But it asks next question also. For example, if you ask ChatGPT, what are the flights available to go to Chennai, suppose, from Durgapur? So ChatGPT will give you the answer. These are the flights available. The next question it will ask, do you want me to book a flight? If you tell me the time of your travel, if you tell me the day of your travel, I can find out the list of flights and then I can give you the best option. What are the next questions to ask? So ChatGPT is a language learning model, LLM model, but it is supposed to be artificial intelligence. So intelligence means it should know what is the next question to ask. And not only the next question to ask, it should also know what is the right action to do, right? And what is the method to control the action. So if you ask the chat gpt to book a ticket to you, I don't know whether it does or not, but as an intelligent system it should be able to book the ticket, right? While booking the ticket, the chat gpt must also realize that it should not take out money from your account without you knowing, unless you give the control, which I hopefully no one will give the control of the bank account to the chat gpt. But if you give the control to ChatGPT, then ChatGPT might be able to book the ticket without consulting you. That is not the right thing to do. So hopefully there is an inbuilt check-in system in the ChatGPT that if you spend something, it will first ask you that are you okay with this transaction? Only then it will make the transaction, because it is an intelligent system. Intelligent system knows what to ask. Intelligent system knows what is the next thing to do, and it also knows what is the right thing to do. So then it is an intelligent system. Okay. So intelligent system, the last thing, the intelligent system, it is not only enough to just analyze the data, that this is the problem, this is the past history, this is the solution, and this is how the solution is to be implemented. Intelligent system, the highest level of intelligent system works on introspection. It is not only enough to give the data, the system must be able to figure out why that solution is working. For example, if you ask the intelligent system, if you ask the system that this is my problem, give me a solution, it will give you a solution. But the system should be able to reason out, should be able to logically come to a conclusion why that particular solution is working, right? What is the solution, why it is working, what kind of problems can come from that solution, and how do we solve those problems. This is the last level of intelligence. So the definition between intelligent and smart. Intelligent, we have seen that intelligent systems are these kind of systems. Okay, it should work in a complex environment. It should be able to sense the data. It should be able to analyze the data. It should be able to introspect. Smart system. What is meant by smart system? Smart systems are the systems which can be programmed so that it is capable of exhibiting intelligence. By this time, all of us might realize that no system is intelligent by itself. You have to make that system intelligent. If a system can be made intelligent, that system is called as a smart system. This is true for human beings also. No person is born intelligent. A person has to become intelligent. A person who is capable of becoming intelligent by studying or by taking a training or by attending classes or whatever, right? If a person is capable of becoming intelligent, then that person is called as smart. So systems which can be programmed so that it is capable of exhibiting some intelligence are called as smart systems. Okay. So this is the part one of the PPT, which we talked about what are intelligent systems and what is the difference between intelligent and smart system. The second part of the PPT deals with little bit of history, that why do we need change. I will talk about what is happening in the present scenario, why do we need to change. We'll talk about the origin of smart manufacturing, data-driven manufacturing, paradigms of smart manufacturing. Paradigms means basically the elements. So paradigms seem to be a more technical word, so I just put it, elements of smart manufacturing. And then we'll talk about industrial internet of things, and then we'll go to the part 3. So the accelerating pace of change, as you can see from as per the recorded history, agricultural revolution to industrial revolution, this change. Someone is asking something.
All of you please mute. All of you please mute.
Shall I continue?
Yes, sir. Continue, please.
Okay. So agricultural revolution till industrial revolution, it took us 8,000 years to go. After industrial revolution, the invention of light bulb, it took 120 years. Invention of light bulb till moon landing, 90 years. After moon landing till internet, 22 years. After internet, human gene sequencing, 9 years. So after human gene sequencing, the cloning, it took maybe 3 years, right? And presently, we all of us are observing, right? Chat GPT, artificial intelligence, these things came maybe 1 year back, 1 or 2 years back. And now our life is completely changed. The way we interact with a problem, the way we do our searches, the way we fix a problem, the way we try to find a solution, everything has changed. At least personally for me, I can tell you, it has completely changed. How I used to search for from Google has completely changed now, right? So the change is happening at a very fast pace. The things are moving at a very fast pace. So example I have given over here, number of years it took for each product to gain 50 million users, right? So when the airline was invented, earlier number of users were very less. So to get to 50 million users, 50 million users is 50 into 10 lakhs. 1 million is 10 lakhs. So 50 into 10 lakh, around 5 crore. So after invention of airlines, to reach 5 crore customers, it took 68 years. And then as we keep on moving, after invention of cars, took 62 years to reach 5 crore. Telephone took 50 years to reach 5 crore. And gradually the time is reducing. So I will come back after invention of iPods. It took 4 years to reach 5 crore. After invention of Facebook, it took 3 years to reach 5 crore. Then Pokemon Go, it is a game, right? I don't have the very current data, but I wanted to put the data of Chat GPT. How many users are there in Chat GPT? It might be 50 million also. And Chat GPT might have reached 50 million very, very quickly. So maybe within a matter of 10 days, I don't know, right? The accelerating pace of change, the things are moving at a very fast pace. Things are changing very, very rapidly, right? One of the major reasons why things are moving very, very rapidly is because our computing power has increased. So there is a very popular meme, a very popular graphic which is there, that the first moon mission that was sent, that Apollo 1 mission, the first moon mission, the computer for the first moon mission has a RAM of maybe 13 MB RAM, right? 13 megabytes. Can you imagine 13 megabytes RAM the computer had? And it was used to send a rocket to moon. And nowadays, using our phone, if you take an image, if you go to an airport and then you go to the bathroom and take a image, bathroom selfie you take, and then you have to put it on Facebook so that everyone knows you are going to such place and so place, right? So if you take an image, that image is 13 MB if it is a very good phone, right? So earlier, maybe 70, 80 years back, we were using 13 MB to send people to moon. And nowadays we have used 13 MB to take a airport selfie, in which we'll get maybe 10 likes and we are happy that, okay, everyone knows I am going to Delhi. So I have taken the selfie. So the exponential growth of the computing power. Computing power, earlier it used to be sacred. Earlier the computers has to be housed in an AC environment. I remember the first time I saw a computer was when my mother, she had to take an X-ray and she had to go to that clinic. It's long back. I was in class 4 or 5, I think. So around 1998 or 1999. Right? That time the computer, the doctor, that clinician, they had a computer. It was a AC room. And I remember thinking that computers must require AC to function. Such was the sacredness of a computer. Computer used to be a big thing. If you are a computer engineer, people used to think you are a miracle person, right? You are such a big person. But nowadays, the exponential power has become very, very common. My phone has a RAM of 4 GB RAM, right? In my BTech, the first laptop that I purchased, it had a RAM of 512 MB Celeron processor, which was state of the art that time. It was a very expensive Lenovo laptop I had in my BTech first year, 2006. But 512 MB was a huge thing. And then progress happened very, very rapidly. So our computing power has gone up. Okay. And the connectivity shift. Earlier, the number of people connected to a particular device was less than one, which means one person was connected to one device or less than one devices. But nowadays, a person is connected to multiple devices. For example, I am connected to my mobile. In my mobile, I have opened my Gmail. In my office computer where I'm giving the PPT, I have opened my Gmail. It has got two Gmail accounts, my personal Gmail and the official Gmail also. Similarly for my mobile. Again, I have opened my personal and the office Gmail in my laptop, the laptop which the college has given. So I am connected to these three. I am also connected to my lab computer, right? So this is for me. A person who is working in, suppose, an office, he might have access to all the computers of that office. If he is in a managerial position, right? He should be able to access all the computers. So that's how the connectivity has shifted. A person has got lot more computing power, and a person has got lot more access now. He is connected to lot many devices. So it is almost understandable that the things has to change. So how things have changed? We have started with industrial revolution, and the industrial revolution has progressed into industry 4.0. The first industrial revolution happened in 1784. All of us know this. After the invention of the steam engine, the industrial revolution happened. Earlier, people used to do very trivial tasks. They used to move machines. They used to take out oil. They used to do normal tailoring and so on, right? The second industrial revolution happened around 100 years later. Second industrial revolution happened with electricity, and second industrial revolution continued till the First World War, and it got a lot of boost. If you study a little bit of history, we can figure out that most of the human progress happened in the time of turmoils, in the time of wars, right? So at the time of war, human beings, they try to minimize the consumption and maximize the output. So it got a boost. The third industrial revolution happened around 40 years after the second revolution. So the third revolution happened during the 1960s, which was the semiconductor based revolution. People invented chips. In the Second World War, people wanted to move towards automation. There are historical reasons for it. In the Second World War, demand was very high, and the factory workers were not available. They had to go to the war. All the men were recruited by the Allied countries, USA, Germany also, there were Nazi countries, USA, Germany, Italy, France, UK. These countries, they were the industrial powerhouses. France, they were industrial powerhouses. But the men who were working in the factories, they had to go to the war, and there were no one else to operate the machines. And then the big industrial people, the industrialists, they did not have to go to the war because they are industrialists. So that time they figured out that having the machines are not enough. Machines should be able to work by themselves. We should be able to write a code and feed the code, and machines should be able to work by themselves. That's how automation started coming up. So the third industrial revolution happened when automation was also automated. That we will not even write the code. We'll just write a program and we'll feed it into a chip, and that program will then run different executions for the but problem one, this is the code, problem two, this is the code, that kind of thing will happen. So that's how the third industrial revolution came. Demand, of course, the population also increased, so demand was very high. Machines were becoming more complex, the raw materials were more complex, and mathematics came up. Before third industrial revolution, actually before the second industrial revolution, mathematics was not so much part of the industry. Industry was supposed to be a domain where everything is done based on knowledge and experience. Now, most of the times the industries happen to be family operated businesses. So everyone had knowledge about those, and they used to do the things like that. That, okay, father has said that you take 10 workers, I will take 10 workers. But then people figured out that no, industrial engineering is the thing. Everything mathematics can be used to solve many of the problems. And then operations research came up. So mathematics came up to keep up with the mathematical idea, to keep up that mathematics is saying that in a day I have to produce 1000 units. To do that, we needed automation also. So that's how the third industrial revolution came up. And presently, the fourth industrial revolution is happening. Fourth industrial revolution is happening because of two things, as I've told you. First is the connectivity has gone up. The persons working in the industry, they are connected to lot many devices, and they have control over those devices. And secondly, the computing power has gone up. And now the big people, the industrialists, the people who are controlling the industry, they are thinking that if we can connect the machines together, if we can control the different aspects of the engineering using machines, using programs, using codes, then we can further improve our productivity. Because the one thing that the industrialists have been wanting to do ever since the time of industrialization is to maximize the profits. They want to improve the profit. How can you improve the profit? If you produce more but consume less. right? So consume less means you take less raw material, which means you waste less raw material. The wastages are minimized. You don't have to employ lot many people. You don't have to give lot of money to the people. These are the things which are appealing to the industrialists, right? They want to improve the productivity, and one of the major limitations of the productivity was the human element. Human beings, we are emotional beings. We cannot function at the same level of efficiency throughout maybe 1 month, right? Today we are happy, we'll function very good. Tomorrow we are not happy, we won't function that much good. So we want to automate those things. Of course, a person will be in charge of it, but the work will be done by some other agents, some smart agents or in the intelligent systems, right? That is called as the fourth industrial revolution. Internet has also gone up, computational power has gone up, and the person has also got access to lot many devices. Okay, so the last three revolution, the motivation was mostly economic. Economic means that the industrialists, they were more concerned with producing more. But nowadays, the fourth industrial revolution, it has become a cultural and societal event also. We want more products, we want the products in a short time, but also we want to reduce the hazards, right? For example, you can see that nowadays we have got e-rickshaws outside. All of you might have observed, right? We don't have the human operated rickshaws. Before the human operated rickshaw in Kolkata, we used to have that the person used to pull the rickshaws, right? Then we got human operated, the person used to pedal it, and then he used to take the rickshaw, and now we have got e-rickshaws, right? So this is a cultural thing also, that the person want to get the output, the person still want to earn some money, but the effort has to be minimized, the effort has been reduced, right? So this is how this is one of the features why the fourth industrial revolution is appealing to the people, that yes, we want to improve the productivity, we want to improve our manufacturing, but we want to reduce the effort also. Okay, so that is how the concept of smart manufacturing comes. This is a definition of smart manufacturing. I've taken it from one or two sources, so I've not given the references over here. If you just put smart manufacturing, you can find this definition normally. Is a technology driven approach. It utilizes internet connected machinery to monitor the production process. It identifies the opportunities for automation and uses data analytics for improving the performance, right? Very simply put, suppose there is a drilling machine, there is a workpiece which is to be drilled using a drilling machine. You put sensors to the drilling machine, you put sensors to the workpiece. The data from the drilling machine and the workpiece will be fed into a system, which is an intelligent system or smart system. That intelligent system will analyze the data that, okay, this is my workpiece, tungsten. This is my tool, which is suppose HSS, high speed steel. HSS has to move in these many parameters. The feed rate has to be this much. The tool rotation has to be this much. The applied load has to be this much, and so on. That data will be fed into the drilling machine, and drilling machine will operate at those parameters. During the operation, when the drill is over, then the drilling machine will by itself, it will retract itself, and then the next location will come. This is the basis of smart manufacturing. Okay. One of the major features of smart manufacturing is predictive maintenance. We'll talk about predictive maintenance because the different slides are there for it. I don't want to repeat it again and again. Okay. When we implement smart manufacturing across the entire spectrum of manufacturing, when I say entire spectrum of manufacturing, I mean right from the raw material stage, right from processing of the raw material, how much raw material is to be sent to which factory, after sending it to factory, where to store the raw material, from the storage unit, how to bring the raw material to the machines, in the machine, which parameters to use, make the part, after making the part, how to take the part and then store it, after storing it, how to put the barcode to the part, then how to transport it outside the factory, everything. That is the entire spectrum of manufacturing. If you can implement sensors, if you can implement internet connectivity, if you can make machines communicate with each other for this entire spectrum, then the productivity will exponentially increase. It will increase in a very, very large manner, right? It reduces the downtime. Machines won't break down. It does predictive maintenance. I will tell about it later. It spots the slower production where the time is being wasted. It can figure out. For example, if you are working in a forging plant, in the forging plant, a major time is wasted while unloading the raw material, because the raw materials are very, very big. There are like 50-ton billets will be coming from some casting industry. So those billet have to be taken down and then cut, and those billet have to be processed in a steam hammer. So unloading those billet will take a lot of time. So if you implement smart manufacturing, this is an observation that I'm telling you. But if you do smart manufacturing, if you make the machines connect with each other, from the data itself, you can figure out that what is going to happen, right? Where the production is slowing down, where we can improve. Again, you can use the data to make simulation model. You can use the data to keep the inventory at an optimum level, and you can use the data to make distribution networks, right? You can figure out the raw material is coming from which plant, how far away is that plant. Depending upon the distance, you can optimize that. Okay, I won't purchase my raw material from factory 1 because it is very far. I will purchase it from factory 2, so that even if the raw material is a little bit low quality, but the money that I'm wasting on procuring the raw material from factory 1 is higher than the money wasted from the low quality. So I will take a decision based on that. How can you make the decision? Based on the data. You have to have access to the data. So why data is so much important? As a human being, sometimes we take decisions based on the past experiences, based on data without even knowing it, right? So there is a very famous incident, many of you might be aware, and those of you who have read, surely you are joking, Mr. Feynman. It's a book written by Professor Richard Feynman. He got Nobel Prize for inventing quantum electrodynamics, right? So he wrote this, surely you are joking, Mr. Feynman, is his autobiography. Okay. So he told this problem that as a kid, he and his parents used to go to a drive-through counter, which means you go in a car and you give the order that, okay, I want this ice cream, and then you go to the next counter, take the ice cream, and then you come back. So they used to do that. So he made an observation that the days where he used to take chocolate ice cream, chocolate sundae, when he used to take chocolate ice cream, while coming back to home, the car used to break down. Some problem used to come to the car. But the day when he used to take vanilla flavor ice cream or mango flavor ice cream or cocoa flavor ice cream, the car did not give any problem. So this was a peculiar thing for the Feynman, for Richard Feynman. So he made an observation that, okay, Monday I am having this ice cream, nothing happening. Tuesday, nothing happening. Wednesday, Thursday, I am having chocolate ice cream, car is breaking down. And he take this data so many times. And every time chocolate ice cream, car is giving problem. Of course, this is not a mechanical problem. He went to the mechanics. He told them that I have got a problem in the car, that when I buy chocolate ice cream, my car breaks down. So mechanics laughed at it. What is this? What you are telling? This cannot be. You go away. He was a kid also. And then he made the observation that whenever he is purchasing chocolate ice cream, after making the payment at counter 1, when he goes to the delivery counter in the car, and if he wants to take the chocolate ice cream, the delivery time for the chocolate ice cream was high, because the person who is making the chocolate ice cream, he used to put molten chocolate, and then using liquid nitrogen, he used to freeze that molten chocolate. So during this duration, when the person is doing all this, the car engine had to be switched off. Feynman's dad, he used to switch off the car, because why to waste petrol, right? And then when they come with the ice cream, and again he switched on the car, and then on the way back, the engine used to shut down. And then Feynman figured out that since the engine is getting switched off, the engine is cooling down, and the cold engine is leading to the future failure of the car, right? So when Feynman found this solution, this is a database solution, right? Feynman took the data that, okay, chocolate ice cream giving the problem, but why chocolate ice cream giving the problem? Because chocolate ice cream is taking more time to getting for the delivery. So that is why it is giving the problem. So Feynman solved the problem based on the data, right? The second incident, it happened during my PhD in IIT Delhi. There is a lab in IIT Delhi which is called as combustion lab. If you ever go to IIT Delhi, between block 2 and 3, there is a combustion lab. So in the combustion lab, what they do is they design propeller blades and they put time versus temperature plots. So some research scholar designed a titanium blade, and the idea is they will put a flame onto the blade, high temperature flame, and they will plot the temperature of the blade. The idea is After plotting, the temperature should come at a steady level, because if the temperature is fluctuating means the blade is having some problem. So a research scholar made the blade, gave it to the combustion lab, they put it into the apparatus, switched on the flame, took the data. Monday, data came nicely. The temperature started at a high value, came down to a lower value, and then it became constant at that value, which is okay. Tuesday, again, the data came nicely. Wednesday, again, the data came nicely. Thursday, data came nicely. Friday, when the experiment was repeated, because every experiment we do replicates to make sure that it is not a random event, right? When he repeated the experiment, he found Friday the data after 3 o'clock, because the experiment started at 9 in the morning, it went till 6 in the evening. So long time experiment, time versus temperature plot. So at 6 o'clock, at 3 o'clock, the graph starts shaking. And from 3 to 4:30, the graph will shake. After 4:30 till 5, again, it will become constant. So he was very intrigued that what is happening. So he told his supervisor that, oh, this is happening. Monday, Tuesday, Wednesday, Thursday, everything is fine. Friday also everything fine. But 3 to 4:30, some problem is there, right? So next week, again, he repeated 4 days, everything is fine. Friday, some problem came. So he went and told his supervisor, sir, you please come and have a look. The supervisor came, he looked at the plot, and sure enough, there was a disturbance. So he told, okay, next week I will also be there. So next Friday, everyone was there. We were also there because we have nothing more important to do. We want to see what is happening on Friday at 3 o'clock. So everyone is there. The data has come in the morning and it has flatlined. The temperature has reduced, and then it is coming at the flat thing. At 3 o'clock, again, the data starts shaking. So everyone is thinking what is happening. Someone is putting some religion angle. Friday data is changing. Something is happening. Some vibrations are coming. But no, that is shut down, right? And then the supervisor figured out that every Friday from 3 o'clock, the garden outside the lab, because it was a ground floor lab, the garden outside the lab, the gardener, he is taking that grass cutter, which is a engine based grass cutter, big garden, so big lawn. So engine based grass cutter he is taking, and the machine on which the plot was being plotted, the flame testing was being done, the earthing of that machine was there in that same garden. It is a chemical earthing. Earthing is of two types, all of you might know, strip earthing and chemical earthing, right? So chemical earthing, you take the wire and you put it into the ground, and there is a vessel in which some chemical is there, which is grounded to the earth. So that is chemical earthing. So chemical earthing was there in the garden. The chemical earthing wires will connected to the machine, and on the garden, the lawnmower used to move. And when the lawnmower used to move, the earthing wire used to get shaken. And because of that, the plot used to vary. When the plot used to vary, people used to think, oh, what has happened, right? And the supervisor figured it out that, okay, this is happening. Then someone went and requested the gardener, please stop. We want to see what is happening. And then he came back. Gardener also came back to see what is happening. So many professors and so many research scholars are there. What I have done. So he came and see that, okay, now the data is stable. And then they figured out that, okay, that is why it is happening. So this thing is also based on a data. The Feynman's incident was also based on data. This particular experience that I have told, all of you might have had such experiences, right? So all of these things are based on data. The thing is, when the data set becomes very, very large, as a human beings, we have a limitation. We don't know what type of information to take from what type of data. When such a problem comes, then taking the data and analyzing it manually becomes very, very difficult. We cannot have the physical model to run the machine. We have to take smart decisions. Our data has to be run through machine intelligence, an intelligent system which can take the data, logically analyze the data, and can take smart decisions based on the data. So this is the reason why smart manufacturing is needed. Okay. This is the framework for data-driven manufacturing. There are different layers. The manufacturing process, the data is fed into the sensor interface. From the sensor interface, the data is fed to the data processing. After data processing, it is data analysis. The data is analyzed, and after analysis, the decision is taken. This particular schematic is again implemented in the smart system, as I will tell you later. Okay, this is the origin of smart manufacturing. I will cut it short because already 12:12. I'll try to finish within 12:30. So 2006, during a conference, people figured out that smart thing has to be done for the future. Around the same time, Germany was coming up with something called as Industry 4.0, which later became Industrial Revolution 4.0. 2010, people gathered and they decided that the chip-based manufacturing has to be implemented across all the manufacturing so that it can be controlled and it can be improved. 2014, German people, they give a standardization roadmap that these are the processes, this is how different processes should function, this is how different processes should interact with each other. One of the major challenges of smart manufacturing is the standardization. In order the different machines are able to understand each other, each of the machine must communicate in the same way. The fact that I am talking in English, you are able to understand English is because English has been standardized. Suppose I am talking in Telugu and most of you might not know Telugu, then it will become a difficult problem to understand. Right? Similarly, standardization is the communication language, the communication framework for different machines across the world has to be same. 2016, of course, US, they made the Smart Manufacturing Institute. Anything which is done in the world, US is the first one to take patent of it, right? And they are the first one to make a committee. They will claim rights for everything. Luckily for us, this smart manufacturing is not claimed by the US. 2017, the Singapore, they came up with a quantitative term which is called as SIRI, Singapore Smart Industry Readiness Index, SIRI. Okay, this is not that Apple Siri, this is something else. So this is a score which the Singapore industrialists, they decided that if an industry is having a Siri rating of this much, then we can call it to be a smart industry. Okay, these are the paradigms, these are the elements of smart manufacturing. If at all we are dealing with smart manufacturing, there will definitely be robotics involved, which will be doing some of the work, as I will tell you later. There will be artificial intelligence involved. There might be additive manufacturing, nano engineering involved. There will definitely be IIoT, Industrial Internet of Things. There will be simulation, and there might be composite materials involved. If these things are involved, or at least one of these things are involved, then and only then we can call that particular thing to be smart manufacturing. So what is IIoT? IIoT is a system, is an ecosystem where every device is connected to each other through internet. Okay, IIoT, it reduces downtime. It makes it easy to track and monitor the goods. It provides condition-based alerts. For example, while transferring the good, if anything is going wrong, if the good is getting spoiled, it will give you information that, okay, you are bringing this shipment of oranges and the oranges have gone bad. So you can take a decision that you stop the shipment. We don't want that those oranges. Okay. It minimizes human errors. Human beings, as I have told you, we are emotional beings. We can take decisions in a good frame of mind. But many times human beings, they cannot function continuously. Right now I drank water, right? Machines, they don't need water. They can function continuously. And whatever errors are happening because of human beings, if you eliminate humans from the scenario, if you put humans in charge of machines and machines are doing the stuff, then the human errors are minimized. Okay. What are the concerns of IIoT? IIoT, first concern is the connectivity challenge. Every device has to be connected to each other, and those connections have to be made, and those connections have to be maintained, right? Living in a city, we might not realize, but making those connections in a remote area is quite a big challenge. Internet has not penetrated in that manner in all the corners of the country, right? Right now, yes, we do have internet, but those are okay only for viewing reels. If you watch reels and you watch Facebook, then it's okay internet. But if you want to connect machines and you want to analyze data using internet, it will crash, right? Second is the security. Anything is there on the internet, we are not sure how much securities anyone can hack into it. Of course, I am a mechanical engineer. I don't understand the more bigger challenges of the hacking, but yes, it can be hacked. And the storing of the data. So much of data is generated. Where do you store that data? And not only storing, the data has to be stored in a manner so that it can be easily retrieved also. So these are the challenges. So that is part 2 of the PPT. Part 3, I will talk about the role of smart manufacturing in mechanical engineering. We'll finish it within 10 minutes, hopefully. Anything you want to ask till here, please do. Or maybe at the end if you feel. Okay. So in mechanical engineering, smart manufacturing leads to predictive maintenance. There are four types of maintenance: reactive maintenance, when anything is going wrong and then you are solving it; preventive maintenance, regularly you are doing something so that nothing will go wrong; predictive maintenance means you are regularly not doing something, but you are regularly tracking it. And from the regular tracking, you figure out, yes, now something is about to go wrong, and then you solve it. So it is the best way of maintenance, in which you are not letting the machine to fail, you are not continuously maintaining it, you are just observing it, and then when it is failing, when it is about to fail, before the failure you solve the problem. That is the predictive maintenance. And the last one is prescriptive maintenance. Prescriptive maintenance is something which we are developing, industry is trying to come up with it. Prescriptive maintenance is, again, you are not looking for failures, you are just looking in the disturbance in the data, you are continuously taking the data, and if you just see any random movement in the data, right, which might not lead to failure, so even then you do the maintenance. That is prescriptive maintenance, but we are still trying to figure out what can constitute it. Okay, so these are some of the examples of smart manufacturing. There is an information network which is connected to the customer side, which is connected to the data mining center, and which is connected to the management side also, right? So there are different layers, as I've told you earlier. Those layers have been implemented in this. So a smart manufacturing scenario has got connectivity like this. This is another example of a smart manufacturing, but the equipment is feeding the data into RFID. That RFID is doing the pre-processing, feature extraction, fault diagnosis, prognosis, and then they are putting the data into the decision-making system. KPIs they are maintaining. They are maintaining the. They are managing the maintenance. They are managing the logistics. Again, the instructions are then again fed into the equipment. This is the entire ecosystem of the smart manufacturing. Okay. So predictive maintenance, it helps you to recover the revenue quickly. Assets are continuously available, lower risk. I have written those things over here. Predictive maintenance enables these things, which are good for the industry. Some real world examples of predictive maintenance. These are the four examples that I found. Rolls-Royce is a car manufacturing company. All of the engines of the Rolls-Royce, they feed the data into a single cloud, right? And it continuously monitors more than 10,000 data points. If 10,000 data points are given to a human being to monitor, it is not humanly possible. The person will be overwhelmed, right? He will either he has to be a genius, but geniuses are not readily available. All the geniuses go to politics. They don't do data science, right? So those much data a genius also might not be able to handle. Normal human beings cannot handle, right? Those data is fed into a system. It analyzes the data, and anytime if any engine is about to fail, the owner is notified that, okay, your engine requires maintenance. Doing this, more than 400 downtimes have been reduced. Earlier, before the predictive maintenance was implemented, before the data monitoring was done, the cars used to break 400 times, which is not a huge number, but Rolls-Royce is used by big people. They don't have that much time. If anything goes wrong, they are very, very troubled. So they want continuous functioning. So Rolls-Royce was able to provide that. It's a luxury car. Okay. NG is a company. So NG is a company, Australia-based company, power plant company. So it uses machine learning-driven predictive maintenance, right? It build models, and it uses those models to train. And using this annually, they are saving 8 lakh pounds every year. This is the data that I have got from the internet. Okay, this is because of predictive maintenance. BlueScope Steel, again, Australian steel producer. A little correction, NG, I have said Australian company. I am sorry, I might have misquoted. I don't know which country it belongs to. Might not be Australia. BlueScope Steel is an Australian-based company. Okay. So using sensors, it takes the real-time data. It takes the vibration of the platform, whatever machines are there, because steel industry, it requires a lot of rollers, a lot of furnaces, steam hammers, your steam engines, and so on. So it continuously monitors the data, and using predictive maintenance, every year around 2,000 hours it is saving. And lastly, Mercedes-Benz, it uses digital services like Truck Live and Uptime to continuously monitor the data, and it avoids the failure. Okay. So the second element of smart manufacturing is assistive tech. So these are the different. This is a animation. This is a cartoon sort of. So which is showing the different elements of a production. So there is a computer, and it is showing the assistive tech, the things which can help a person to function better. For example, a person who is checking the workpieces, he is aided with a computer vision. So this example you can see in airports when the bags are scanned. A person does not have to manually open the bag, right? You can just pass the bag from that X-ray, that thing, conveyor belt, and they can see what is inside. Machine analytics, the person does not have to analyze the things by himself. The computer programs will help him, right? IoT based sensors, you can make use of industrial Internet of Things to see from where to get the raw material, from where to send the finished product. He is doing smart packaging. The unmanned trucks are moving, which are controlled on a which are moving on a fixed path, which are moving quickly also. Cobots, which are cooperative robots, they are handling the work pieces, right? Unmanned aerial vehicle are there nowadays. You might know in Bangalore they are delivering using drones. They are making home deliveries using drone. They are delivering some other things also, which I cannot mention. So that they're delivering over here. Things have moved to that level. Okay, and then augmented reality. This is something which is a little bit of science fiction right now, but we are getting there. That the entire plant will not be in a chart or in a computer, it will be in a display, which will be there in the air. And then with that display, you can interact. But we are getting there. Other than industrial augmented reality, all of these things have been already been done. It is existing. This is just a matter of scaling it up, okay, and making it suitable for heavy duty mechanical industries. Right? We have got collaborative robots for welding, packaging, lab analysis, machine tending, which means screwing and unscrewing the machines, assembly, pick and place, so many things. These things we can done using robots. And these are the different sensors which are an integral part of smart manufacturing. I have told you that you take the data. How do you get the data? We can get the data by using sensors. These are the most basic type of sensors, very, very easily available. And we have made rapid progresses, as you will be hearing from other speakers also, speakers from electronics and other disciplines also. We are making good progress, and the sensors are cheaper now, right? Sensors are much more functional, sensors are much more cheaper. As a mechanical engineer, our job is to figure out which sensor to use in which scenario, and how do you integrate those sensors. If today I ask a proximity sensor, I can purchase it from Amazon, right? But if I want to use that proximity sensor with the embossing device that we have made in our lab, I don't know how to connect it. Then I have to do R&D on it, right? The connectivity is the problem. Okay, this is again another schematic to focus on the smart manufacturing. Then there is the digital twin. Digital twin is a digital version of a real world component. For example, if you want to analyze a turbine, or if you want to figure out how does a turbine behave in which parameters, then you don't have to put the actual parameters on the actual turbine, because the turbine might break down, and turbine is very, very expensive. If it breaks down, then it's a problem. So what we do is we convert the physical thing into a digital version using all the data and everything, collecting all the data and making a model, and then we feed the information over there, right? So it collects the data, analyzes data, runs simulation, visualizes insights, make decisions, and then optimize the production. So this is called the digital thread, the connection between the digital twin and the physical thing. Okay. So this is an example like a plane. If you have watched the movie F1, so there in F1 industry also we have the digital twin. So rather than running the car in the actual scenario and consuming so much of fuel, consuming so expensive tires and engines, we run it in the simulation. I mean the drivers, they run it in the simulation, and then they figure out what is happening. Similarly, for flights, we have got the simulation. Before flying the actual thing, you run the digital twin. So Airbus, they do digital twin. Volvo trucks, for figuring out the shape of the nose of the truck, they do digital twinning first, right? They figure out what should be the shape so that the aerodynamic losses are minimized. Then they produce that shape. Of course, you can understand doing it in the real world scenario will be very, very expensive, right? So we do the digital twinning first. Benefits: operational efficiency, cost reduction, risk management, predictive maintenance, and product quality. Challenges are data management. So much of data is there. Handling that data is very difficult, is very complex. Integrating with the existing systems. Existing systems have been there since 1770s, and things have changed over the time. But presently, if you say anyone that you want to make a self-driving car, they will be very skeptical. A self-driving car, what will happen if the volunteer comes and stops the car? If the car does not stop, then how the volunteer will stop that person and take whatever he wants to take from there, right? How to do that? So there is a hesitation, there is a reluctance in the industry to opt for the smart thing. Integration is a big problem. High implementation cost, as I said, and rightly so. Most industrialists, they are concerned with the cost. So if you propose something, no matter how groundbreaking it is, unless it is beneficial to them in some way, at least it should provide a good image to them. If not money, it should improve their image. So you do something which they can claim that, yes, I have contributed to humanity. If you invent something like that, then they will do that. But if you invent something like a smart car, then you have to justify the cost. That if you implement it, the cost will be good. Scalability issue. Industries are widespread. Industries are big. Doing these things, doing most things are easier in a smaller scale, and which is the biggest challenge that we face as an academician, as a teacher. I can tell you, there are many things that we can do in the lab, but when we try to scale it up, then there is a big problem. Right, as I told you, hot embossing. I work in polymer processing, so I have made a machine for hot embossing of polymers. I can make structures on the polymer. For that, if I want to make it smart, I can take the tactile sensor. I don't know how to implement it. I don't know how to integrate it. Maybe I can take help from one of the experts of electrical department or electronics department. But even if I solve that problem, if I go to the industry, they tell them, I have got this solution, you take it. They won't take it because they want a scalable solution. Scalability is a big problem. Okay, skill gap. Not many people know how to work with the smart system. They are very reluctant for that. And security concerns. Anything which is run by a chip is very difficult to be accepted, because if anything is run by a chip, it can also be stopped by a chip. That is the thing that people believe, or I don't know, rightly believe or wrongly believe. Hacking, you have to find out from the experts, other experts. I don't know how easy it is to hack, but that is a big problem, bigger problem. Okay, conclusions. Requirements are changing. Industry should respond. Capabilities have increased too. So industry can respond. It is T double O, supposed to be T double O. It is a typo on my part. Okay. Capabilities have increased also. So industry can respond. Initially, cost and risk will be high. Resistance is very high. But with proper implementation and approach, the productivity can be improved. So I will stop here. And anything you want to ask or discuss, please do. This is all from my side.
Thank you very much, sir, for your wonderful session. Your practical, example-oriented explanation have surely made our students to learn the concept in an easier way. We are truly privileged to have benefited from your wisdom and knowledge in the domain of intelligent system and smart technologies in manufacturing. We are also thankful to you for giving us your valuable time for the benefit of our students. And now from the participants, if you have any query, you feel free to clear your queries from Dr. Goswami. Anybody please come forward.
Not only queries, if you want to add something, that also you can tell.
Yes, sir, that is also welcome. Please, participant. Okay, so thank you all, and a special thanks to Mr. Sajal Chakraborty of CSE department to take all the trouble to provide continuous technical support to have the trouble-free session. And by this, we have come to the end of the first technical session. So dear participants, I request you to have your lunch and stay tuned with the second session at 3 p.m. on from passive dampers to intelligent control system, evolution of structural vibration control for intelligent and smart structure. by Dr. Deeptesh Das, Associate Professor, NIT Durgapur. So thank you all. Thank you, sir.
Thank you. Thank you. I'll leave now.